In this video, we are going to look at extending upon our knowledge of limits, which is our kind of introductory spot we're in regards to calculus. Today we're going to look at the second option down here. We've already looked at this in the first video. How do we read limits from a graph? Today we're going to look at how do we determine limits when we don't have graphs in front of us. How do we actually calculate them? Pencil and paper calculations. So there's a couple things we got to be aware of. There's two types of situations. The first one is where simply what we call direct substitution. So you take this situation, for example, and if I was to put -2, actually I know x approaching -2 means that x is not actually equal to -2, it's close to -2. However, if I was to substitute it in this example here, you would see, up a bit, I would put an equal sign here, and if I put -2 in here, -2 squared minus 2 times -2 plus 1 divided by -2 plus 3, I would get 4 plus 4 plus 1 over 1, 9, and that would be the answer. So if you can substitute what you're approaching for your variable and you get a number, that is the answer. It's that easy in that case. For example, go over this one. 16 minus, put 3 in where the x is. 16 take away 9, 7. So that's called direct substitution. I wish they were all that easy. As you can guess, it's probably going to be a little bit more difficult than that. However, that's the starting point. You always try and just substitute directly, and if you get a number, that's the answer. It's that easy. All right, on to the next scenario. So the next scenario is when you try to do direct substitution. However, direct substitution leads to what's called the indeterminate form. And the indeterminate form is what's referred to as the situation where the numerator gets equal to 0 and the denominator gets 0. Or this is also considered indeterminate if you had infinity over infinity. So those two situations are referred to as indeterminate. Well, if these turn out to be indeterminate, you need to draw upon your skills from the last 11 years of schooling to try and figure out a way that maybe you could manipulate what this expression looks like so that something will cancel out, something will simplify, and the expression will look a little bit different. You'll see what I mean by that as we get going. But it's going to rely upon your ability to factor, perhaps get common denominators, rationalize, maybe use a trig identity, expand and simplify, expand. Those are the most common things you'll run into. So these are all skills that you've accumulated over your high school career, and we've really kind of concentrated on them in our pre-calculus courses. So let's go over here to this first one. Is that right now, if I look at it, so let's suppose I was to take -2, because x is getting close to -2, and I actually put -2 in where the x is. Well, I'm not going to put it underneath here because I just want to leave that for space to work. If I put -2 to the 4th power, that's going to be 16 minus 16. The bottom is going to be -2 cubed. It's going to give me -8 plus 8. Oops, I want to hit there. So delete that. All right, let's try that again. So when I then add those up, the numerator is 0 and the denominator is 0. That is what I mean by the indeterminate form. So what will happen in this situation is we're going to have to rely upon these set of skills here. So I'm going to go over here and look at this one and say, well, I wonder if there's anything I could do with that. Well, if I look at the numerator, that's clearly difference of squares factoring. And if I look at the denominator, that's definitely sum of cubes that we learned in our last unit on polynomials. So let's just take this and see where the factoring will go with it. Now, the notation for these is the limit part here. I know some students, they hate to write it out there because it's a little bit of extra work, but you need to write that down until you get to the point where you'll actually substitute a number in for the variable, which I'm not ready to do yet. I did it over here just to see that I get 0 over 0. All right, so x is going to approach -2. And we're going to factor the numerator. So that's going to give me x squared minus 4 multiplied by x squared plus 4, difference of squares. The denominator, sum of cubes. Cube root of the first plus cube root of the second. Square this one. Product of these two with the opposite sign. And then square this one. All right, so I kind of look things over, and still nothing here will cross out. Ultimately, you're trying to get things to cancel out, factors that will cancel out. Nothing cancels yet, but this one, if you look at it, that's still factorable. This will factor down to difference of squares. And it almost becomes like playing the game of chess where you kind of look 2 moves ahead and say, oh yeah, well, if I keep factoring this without even writing them down, I can see that the factors are going to be x subtract 2 and x plus 2. And those two x plus 2 factors are going to cancel each other out. So let's continue with that. Limit, difference of square. Don't forget my x is approaching -2. X subtract 2, x plus 2. Leave this one still there, x squared plus 4. That's going to all be divided by x plus 2 and x squared minus 2x plus 4. So you can see here that the primary skill I've relied upon is my ability to factor. And if you say, oh, I'm not very good at factoring, well, you can obviously see you're going to run into some problems doing these types of questions. It's just kind of understood or assumed that any student that gets to this point in their math career where they're doing limits has mastered this set of skills over here. And again, I know some of you probably would like to be a little bit stronger at these than you actually are. You're going to get some practice doing limits to improve upon those. Now, if I go back over to here, notice you have an x plus 2 factor in the numerator and you have an x plus 2 factor in the denominator. And if we were to think about this, if x was equal to -2 in here and here, those are clearly the 2 factors that are causing us problems because that one is equal to 0 and this one is equal to 0. So if I'm able to cross those two out now, that will fix our problem because now it's not going to be 0 in the top. So now, notice here, I'm going to put -2 in for the x's. So I don't need to write lim anymore. I'm just going to put equals -2 minus 2. So that bracket's minus 4. -2 squared, that's 4, plus 4. Denominator, I've got -2 squared, that's 4. -2 times -2, that's plus 4. And then plus 4 there, giving me a final answer. So this is 8 times -4, that's -32. Those 4 had to give me 12. This fraction will reduce. I could divide everything by 4. That'll give me -8 over 3. So I relied upon my factoring skills. I ended up with no longer, so you can see here, once I did my substitution now, I did not get 0 over 0 like I did in the beginning. And the reason for that is because I got those 2 factors to cancel each other out. All right, let's have a look at this one. So over here, and in some of these questions, you've got multiple options. You might do it one way, I'll do it with a different process, and we'll ultimately end up in the same spot at the end with the same answer, we hope. Putting 0 in for x, if you look at that, And you can eventually maybe even just do, you don't have to write this out over here. You can do it in your head even. So I'm just going to, but I'm going to write it out for now. So if I put 0 in there, I'm going to get 0 times 0. So the numerator is 0. Now the numerator being 0 by itself is not enough. You have to get 0 over 0. Put 0 in here, I'm going to get 2 squared, which is 4, minus 0 in here, you're going to get negative 2 squared, which is also 4. So 4 minus 4, I do get 0 down there. So this is indeterminate, which means we have to try and use some skills that we have in the revolving algebra to try and fix this problem. So I'm going to rely upon definitely some factoring here, greatest common factor. Down here, you really got two choices. You could square both of these binomials, collect all the like terms, and factor that expression, or you can recognize that this is something squared, subtract something squared, which is basically the process you used over here, except they're binomials instead of monomials. So I'm going to use difference of squares and factor the bottom. All right, this is what it will look like. So limit, take out your x in the numerator, leaving you with x onto x plus 3. X is approaching 0. Denominator, now difference of squares. So the square root of something squared is just whatever you're squaring. So there's square root of the first. Subtract square root of the second. That's one factor. And the second factor is square root of the first plus square root of the second. So at this point, there's still nothing obvious that I'm going to be able to cancel out. I'm hoping that this factor is going to cancel out because x is going to 0. So if that doesn't get eliminated here, the numerator is definitely still going to be 0. So hopefully one of these factors in the bottom, when I tidy it up, will turn out to be have a factor of x in it. So we'll leave the numerator, nothing else I can do there. But in this bracket, I could go x minus x, those are 0. 2, subtract the minus 2, that'll give me 4. So that's the first bracket. It's actually now just 4. X plus x, that is 2x. And then 2 plus a negative 2, well, that's just 0. Perfect, exactly what we hoped would happen. These are all factors now because they're multiplied together. This is a factor because it's multiplied by this expression. That, we'll cross that out. Leaving us with, so now I can go equals. I don't need the limit anymore because I'm going to put 0 in for the x. So 0 plus 3, 3. In the denominator, there's nowhere to substitute x. All that's left is this 4 multiplied by 2. That would be your final answer, 3 over 8. Now, another way you can do these, which we're not going to spend any time on, but technically you could take your phone, those of you that have Desmos as an app on your phone, you could type y equals, put this whole expression in, getting all the brackets and everything in the right spot, graph it, and then look at x is 0, and kind of look at your graph, and you would notice that when x is 0, the graph is getting close to 3 over 8. So you can use technology as an option as well. Now, that's not going to be your focus, but I suggest it as maybe a way if you're stuck and if you got an answer and you're wondering if you did it right, use Desmos on your phone and use that to verify your answer. All right, so the first two examples that we looked at, you'll notice that factoring was the strategy that we used to kind of get us through those two. Now, that is not always the case. So here's a couple more examples, and you'll see that factoring is not necessarily our strategy that we use. So if I look at this one, let's try putting 2 in here for x. So if x was a 2, it would be 18 minus 2, which would be 16. The square root of 16 would be 4. 4 take away 4. This isn't my way here. So 4 take away 4 would give us 0 in the numerator. Two take away 2 would also be 0 in the numerator. So direct substitution leads to 0 over 0, which we refer to as indeterminate. So there's no factoring obvious here, no difference of squares, no greatest common factors, no simple trinomials, none of that stuff. So we're going to need a new plan. Well, it's usually when you've got a radical in here, you can almost be guaranteed that you're going to probably have to use the strategy of rationalizing that we would have covered in pre-calculus 11. So I'm just going to get rid of my 0 over 0. And the way this works is you'll hopefully remember the process called rationalizing. Now in grade 11 we rationalized the denominator. It was always rationalized the denominator. Well, in these situations, you may, in fact, rationalize the numerator. It just depends on where the radical sign is. So in this one, it's in the numerator. So rather than me rationalizing the denominator, we're going to rationalize the numerator. So we have to remember how that process works. Well, the first thing you got to notice here in this one is that there are two terms. So 4 would be a term, and then this radical would be your second term. So that's a binomial. To rationalize numerators or denominators, when you're dealing with binomials, you have to multiply by what's referred to as the conjugate. The conjugate is the exact same binomial, except the sign between them changes. Therefore, I am going to multiply the numerator by 4 plus the square root of 18 minus x. That is considered the conjugate of that. Well, you can't just take a fraction and multiply the numerator by some value unless you multiply the denominator by the exact same thing. So whatever I multiply the numerator by, I also multiply the denominator by the exact same expression. Now the reason you have to do that is because if you think about this, what I have in red here, 4 plus the square root of 18 minus x divided by 4 plus the square root of 18 minus x, that is nothing more than just the number 1. If I take some expression and multiply it by 1, it's not going to change the value of anything. What it is going to do for us, though, is change the appearance of it so that hopefully we'll get some things here to cross out. And looking ahead, this x minus 2 is our big issue, because as long as that's sticking around, as soon as I put 2 in for x, the whole bottom's going to become 0, and that's not going to be good. So hopefully, expanding the numerator is going to lead to an x minus 2 factor. So let's see where this all goes. So we've got our conjugate here. Now we're going to expand. So the limit as x is approaching 2, multiply these two. So 4 times 4 is 16. Now, hopefully you can remember from your prior work that when you multiply conjugates, the middle two terms always give you 0. So you don't have to go, technically it's this times this one, and then the 4 times that one, then this radical by 4, and then this radical by this radical. Well, the two middle ones, when they're conjugates, always sum to give you 0. So you don't have to bother doing that. You just go 4 times 4 is 16. Negative times positive is always going to be negative, because these are always going to be opposite signs. The square root of something by the square root of the exact same thing will just give you the expression without the radical on it anymore. That's now your numerator. If you're rationalizing the numerator like we are here, expand it out. Do not expand the denominator. Just leave it as two separate factors. X minus 2, there's your first, put that in brackets, and now just put a bracket around this and write it underneath here as 4 plus the square root of 18 minus x. And again, reason for that is because I'm looking to get this factor to cross out. So I don't want to expand it in here, because then all of a sudden I don't have that factor anymore. When I expand and now simplify the numerator, I am hopeful that I'm going to get x minus 2, or even 2 minus x would be fine. 16 minus 18 is a negative 2, and then a minus, we'll go in here and make that a positive x, so the numerator is in fact x minus 2 after I clean everything up. The denominator is x minus 2. This. As you get more comfortable with these, you'll kind of anticipate what is supposed to happen, and then if it doesn't, for example here, if you went through all this and these didn't cross out, I'd be concerned that I did something wrong here in my expanding or something, because it pretty much is what's going to happen every single time. So we anticipate what's supposed to happen, and then if it doesn't, we can find a mistake. So here, exactly what I hoped would happen did. Take out, I'm just going to now divide that and that. They cross everything out, so everything's gone in the numerator. That means there's just a 1 left there. Now putting 2 in here, because this is a plus, it's not going to give us the 0. It's going to be 1 over 4 plus, if I put 2 in there, it's going to be 18 minus 2, which is going to be the square root of 16. and that is a 4. So when you add those, there's your answer. 1 over 8 was not 0 over 0. All right, so there our strategy was rationalizing the numerator. If that question had been the complete reciprocal, all I would have done is rationalize the denominator. It would have been the exact same. Okay, let's go to this one. So when I go to this one, now what I notice is that it's not, there's no factoring. Don't see any radicals. Well, so the strategies I've used so far do not appear like they're going to help me in this question. One of the things I listed on that last page in terms of strategies was common denominators. With experience, again, these become quite obvious. This one, as soon as I see fractions within a bigger fraction, almost always you're going to find a common denominator. So I'm going to take the 2 fractions in the numerator. I got ahead of myself. I better check and show you that it's actually 0 over 0. So if I put 2 in here, a half minus a half, 0, 2 minus 2, 0. I find sometimes we'll get bad for that because 99% of the time they're indeterminate if they're put on some kind of a test or exam or something. But every once in a while, a teacher or a professor will throw one in there where all you had to do was fill the number and you would have got the answer, which was not the case here. So we have to do something about this indeterminate form. So as I was saying, when there's fractions within a bigger fraction, take the numerator and just get the common denominator of those 2 fractions. So if you have 1 over x and 1 over 2, the common denominator is 2x, just the product of those 2. Well, this fraction, in order for the denominator to become 2x, I'd have to multiply the numerator by 2. This fraction, to have that as its new denominator, I'd have to multiply it by x. So that is now the numerator. Well, technically, that would still be over x minus 2. A fraction divided by something can be rewritten as the multiplication of the reciprocal. So I'm going to just take this now and take the numerator, 2 minus x over 2x, and I'm going to multiply it by the reciprocal. So instead of x minus 2, which is technically over 1, I'm going to multiply it by 1 over x subtract 2, which is going to help us because if you see here, I have x subtract 2 and 2 minus x, which we've looked at before. I've showed you with numbers. So if I just come over here for a second, let's say I use 3 take away 10, and then I have 10 take away 3 on the bottom. Well, 3 take away 10 gives me negative 7. 10 take away 3 gives me 7. When I divide those out, I get negative 1. So if I have any 2 terms or numbers, letters, variables, expressions, whatever they are, subtracted in the opposite order, you can quickly just cross those out and you know the answer is going to be negative 1. So for example here, when I see 2 subtract x and x subtract 2, I can cross those out and know that they're going to always divide and give me negative 1. Now again, that's only true with subtraction. So sometimes students only get half of what I'm saying here, and they'll have 2 plus x and x plus 2, cross them out and put a negative 1. It's not the case with addition. Think about it. If you had 3 plus 10 or 10 plus 3, you're going to get the exact same thing here. They're not going to be opposite signs. So in that case, they'd cross out still, but you'd get a positive 1, not a negative 1. All right, so those are gone. And as you can see, those 2 factors, those were the problem. Because when x was 2, if you put it in here, 2 minus 2, you were getting 0 there. 2 minus 2, you were getting 0 there. They're now gone. Problem solved. Put your equal sign back in here. Numerator, all that's left is negative 1 times 1. So negative 1. X is 2. So the bottom is going to be 2 times 2, giving you a final answer of negative 1 over 4. So those are some good examples to show you the different strategies. So you can see that I relied upon, in this example here, we relied upon common denominators. In this example, our primary strategy was rationalizing. Just jump back here for a moment to the first 2. Now both of these relied upon our factoring strategies. GCF here, difference of squares here, difference of squares twice here, sum of cubes. all factoring strategies that we're supposed to have accumulated over the last, in particular, 2 years of high school math. All right, so that just kind of shows you how you're going to go about dealing with limits that are indeterminate, which, as I've already stated, that is going to be the case the vast majority of the time. All right, so I'm going to put a couple up here at a time. Now, you might want to pause the video and write them down and try them on your own first. And then I'm going to go through the solutions here now with them. So just kind of maybe pause the video, try them. If you get stumped or if you get an answer, play the video and see how you made out. Okay, so let's look at the first one. The first one is, and notice at the top here, I put these ones are tricky. These would be ones that a lot of times students would get stumped on. The first one. So sometimes students say, oh, look, it's a radical. I'm going to use rationalizing. Well, the problem is it's not a square root, it's a cube root. So we do not have any process that you've ever been shown to rationalize the denominator or numerator of a binomial expression with cube roots. So that's not going to work. Having said that, this up here, x minus 8, it will factor. Now students will say, how does it factor? It's not difference of squares. There's no GCF. It's not a trinomial of any sort, so none of those strategies are going to work. Here's the thing we have to make sure we understand, is that the processes of factoring that we know will work for any exponents. They just work better. For example, difference of squares works better if this is a perfect square and this is a perfect square. But there's nothing to say that I couldn't factor this and say, oh yeah, I can factor that. It's square root of x minus square root of 8. That's square root of the first minus square root of the second. Square root of x plus square root of 8. I've done difference of squares, so that's the pattern. But these weren't perfect squares. So this looks kind of messy, but it still follows the pattern and it would still be correct. Well, I don't want to do that because that doesn't make a factor the same as this. However, if we get rid of that stuff, think this through and say, well, how could I get a cube root? Oh, rather than difference of squares, how would I do difference of cubes on this? So what I do is, as x is approaching 8, I do the pattern for difference of cubes, which does this. It says take the cube root of the first. Well, if it's just an x, the cube root of x is cube root x, which that's good because it matches up with this one. Minus, and what's the cube root of 8? Well, it's 2. Well, already that's a really good sign because that's exactly the same as this expression down here. Square this one. Now, these get a little ugly when you write them out, but it's the cube root of 8. So you square the first one. You multiply these together and switch the sign. And then you square that one. That's the pattern of difference of cubes, which you're supposed to know. We did it on our unit on polynomials this year. Well, I don't want to touch this one because it's already the same as that, and we're just going to cross these out here in a moment. Look at that. Perfect. That's gone. Now I can put 8 in here for all these x's, and I'm not going to get 0 over 0 anymore. I kind of got ahead of myself, didn't check. It was 0 over 0 in the beginning. Cube root of 8 is 2 squared. That's 4. Cube root of 8 is 2 times 2. That is also 4. There's already a 4 waiting there at the end. So this and the bottom, I crossed everything out. So it's a 1. 4 plus 4 plus 4 is 12 over 1. Answer to that limit would be 12. All right, on to the next one. X to the negative 2 minus 3 to the negative 2 over x minus 3. Well, that's kind of odd looking, especially these exponents. So this question is kind of thrown there to disguise fractions. If you can recall from grade 10, negative exponents is a way to hide what are called reciprocals. So to do this question, let's back up for a second. 3 to the negative 2 minus 3 to the negative 2, 0. 3 minus 3, 0. So it's indeterminate. All 4 of these are going to be indeterminate that we're going to go through. So the limit as x goes to 3 I'm going to change these from negative exponents to 1 over x squared minus 1 over 3 squared. You take the reciprocal and you make the exponent positive. All that over x subtract 3. So now if we think about this and say, well, does this look somewhat familiar? Yeah, it does. It looks like the last one we did before we just came to this slide. It's a fraction, subtract a fraction within a bigger fraction. So what I told you is that that almost always is going to rely upon common denominators. Well, let's do that. See where it takes it. And sometimes you might try something and it takes you into a mess. And say, oh, that wasn't a good choice. Erase it. Try something different. I'm going to get a common denominator of these two fractions in the top. Well, x squared and 3 squared. So 3 squared is 9, and that's x squared. So the common denominator is the product of those two. So for this denominator to become x squared, I'd have to multiply the bottom by 9, which means I got to multiply the top by 9. For this 9 to become 9x squared, I'd have to multiply by x squared, multiply the top by x squared. As we get a little more experience with these, so technically this is going to be over x minus 3, but we know then that instead of dividing by x minus 3, we're going to multiply by the reciprocal, which would be 1 over x minus 3. It just saves you a line. Well, I kind of look things over here. Say, well, I don't see anything that will cross out yet. However, 9 minus x squared should kind of jump out at you and say, well, that still can be factored now. That would be difference of squares. And if you think about it, before you write the factors down and go any further, 9 minus x squared factored would be 3 subtract x multiplied by 3 plus x. You say, well, did that help me? Sure it would, because you have an x minus 3 here and a 3 minus x. You're going to be able to cross those out. That will fix our problem. So let's do that. Let's factor this out. Some more with them. So this will be limit as x goes to 3. Factor this, difference of squares, 3 minus x, 3 plus x, divided by 9x squared, multiplied by 1 over x subtract 3. Well, we just talked about this a couple of examples ago. X subtract 3, 3 subtract x. You can cross those out. They are subtracted in the opposite order. You just have to make sure you realize you're not going to get 1, you're going to get negative 1. Now, put 3 in for all the x's. So you got your negative 1, 3 plus 3, that's 6. So you have your 9. 3 squared is also 9. So now I've got negative 6 over 81. That reduces, they both divide by 3. So it's negative 2 over 27. And that would be your final answer. So what throws students off in that one is that the question's created in such a way that it hides these fractions that you see here with these negative exponents. So if this had been the question, we would often get a lot more success of the students because say, oh, well, he told us that when there's fractions within a big fraction, get common denominators. But the problem is they don't see that unless you have a good grasp of negative exponents and realize that those can be changed to this. So that's what makes that one a bit of a tricky one. Okay, a couple more. This one's not so much tricky in that it's just a little bit more labor intensive. It takes more work to do this one, and sometimes students don't see the process that'll get them out of that. Putting 1 in here, 1 cubed is 1 minus 1, 0 on the top. Putting 1 in here, I get 1 minus 1, that's 0. A minus 4 and a plus 4, that's 0. So this is indeterminate. Well, hopefully when you look at this, you say, I see a bunch of factoring I could do here. This is definitely difference of cubes. So I'm going to use that to factor that. And then we may look this one over and say, well, I don't really see anything right away. There's a couple ways you could do the denominator. You could do it out using the factor theorem, where you do the trial and error synthetic division, like we did in our polynomials unit. Or you can do factoring by grouping, whichever you would prefer. We haven't done a whole lot of factoring by grouping, so I think I'll do it out the way we did it in the last unit. I'm just going to, before I write this out, I'm going to take this expression because I know it takes a bit of work, and I'm going to factor it out. So x cubed minus x squared minus 4x plus 4. And I need to find something I can put in here for x that will make this equal to 0. So let's try x equals 1. So if I put a 1 in here, which we know gives a 0 because we already checked it up here, so it's 1 minus 4 plus 4 equals 0. So remember, that means if you substitute 1, x subtract 1 is one of the factors. So then we do a synthetic division. So x minus 1, we want to see what we get when we divide this by x minus 1. So we're going to get, sorry, don't put any, put a, just your coefficients. So 1, negative 1. Remember, these have to be in descending order, just the coefficients. Negative 4, positive 4. That number comes straight down, multiply, subtract, multiply, subtract, multiply, subtract. Perfect. I need to get a 0 here. Okay, so when we come back and say, what do we got now? So this would give me the factors. I had x minus 1 from earlier. X minus 1. This was x cubed. So when you do your synthetic division, this is always 1 degree or exponent lower than this one. So this is now going to be x squared. There's no x term. Minus 4. The good news is that factors. So we got x minus 1, x subtract 2, and x plus 2 because we do difference of squares on this one. So these three are the factors of this. All right, so I'm just going to take, I'll come over here and rewrite this question now that I've done all that work to factor the denominator. And if we look at the original question, it was x cubed minus 1. So difference of squares on that would be x minus 1. Square this one. Product, opposite sign, square this one. The factors of this, we did all this work over here. And the only reason I did it off to the side is because I knew it was going to take a fair bit of work to get these factors. And I didn't want to keep writing out limit over and over, write it as a fraction, so I just did that kind of off to the side. So I have these three factors now, x minus 1. So as we're writing them down, your eyes should light up and say, great, because those two are going to cross out. They're the ones causing me the problems. X minus 2, x plus 2. That gets rid of that. Now, direct substitution, we should be fine. 1 squared is 1, plus 1, plus another 1. Put 1 in here, 1 minus 2, negative 1. 1 plus 2 is 3, leaving me with a final answer of 3 over negative 3, which is negative 1. So that one took quite a bit of work to get to our final answer. So that's why that one I would say is a bit tricky. A lot of times students say, oh yeah, I forgot all about that whole process that we did in polynomials. Unfortunately, when you get to these kinds of courses and these calculus concepts, it's just assumed that you have mastered all of that content in terms of factoring. All right, so we're out of room for this one. Let's put it on a new page. Take that. That. All right, so let's look at this one. So what makes this one a little bit different is that it's completely variables. There's no numbers in it. So students say, well, what if h goes to 0? Well, if I put 0 in there, I'm going to get a squared minus a squared. That's 0. If I put 0 in there, clear to the bottom is going to be 0. So it would be 0 over 0. Well, what are we going to do with that? Something squared, subtract something squared. That is the pattern to factor using difference of squares. So I'm going to factor the numerator using difference of squares. Let's see where that takes me. So if the square root of the first, this is all considered the first. So the first squared, take the square root of that, you're going to get a plus h. Subtract square root of the second, which is just a. There's your first factor. Square root of the first, a plus h, plus square root of the second. Everything is over h. Limit as h goes to 0. here now I've got a plus h minus a. Well, all of that, when you tidy up that bracket, is h. A plus a is 2a plus h. All of that is divided by h. Well, those cross out. Perfect. That's the problem. That was because h is 0. That just gives me a 1 there and a 1 there now. And now if we make h go to 0, I'm going to get 2a plus, so h is going to become 0. And the answer here is, rather than a number, it's an algebraic expression. It's 2a. So the limit of that expression up there as h goes to 0 is 2a. So that would be one where putting it on Desmos and graphing it probably is not going to be an option, because these variables you're not going to be able to put in and come up with an actual graph on a grid. All right, at this point, we arrive at a checkup slide on limits. So I'm going to ask you, when you get to here, to stop the video. Hopefully you have this downloaded on your phone, tablet, computer, whatever it may be, and just look through it and jot down what you think the answers are. So it scrolls down. There's a couple questions here. And you're going to answer these questions. This would be something that I had used kind of as a quiz before, just to see if students have grasped the concept of limits up until now. So it's kind of a checkup for yourself to see if the material in the video you've actually understood. Okay, so I want you to take a few minutes, go through these questions best you can, turn the video back on, and I will have the solutions for you. All right, here are the solutions for this checkup quiz that we've got. Now, the graph is a little faint over here. This was all connected, supposedly, and then this was connected here, too. So that's like a dot. And then we got an open circle here and an open circle here. All right, so I wanted to find the limit of this function over here as x is getting close to -2 from the right-hand side. -2 coming from the right-hand side. I'm hitting the graph right there, which means on the y-scale, we're getting close to 0. +2 from the left-hand side. So the left-hand side, you're hitting the graph down here, which is close to -1. That's a -2. So it's getting close to -2 on the y-scale. So it says, what's the limit of this function as you approach +2? Well, it doesn't stipulate here left side or right side, which, if you remember in our video number 1, this means you've got to check both sides. Left side, we just did. It's down here. Well, here's the problem, though. If I go to the right side, there's nothing over here. You hit the graph up here. So when you hit the graph up here, you're getting close to 1, which means that the left side and the right side of 2 are hitting the graph in 2 different places, which means this does not exist. Then it says, what is the function at the number 2? Well, that means if you're actually not just to the left or just to the right, what if you actually pick the number 2? Where do you hit the graph? Well, it's not there because there's an open circle. It's not there either because there's an open circle. That means you would never hit this graph anywhere, which would make this one also does not exist. Okay, so that's reading limits from graphs. All right, so let's look at these. Hopefully I can fit these on the page here. First one, putting in x is 0, you get square root of 4, which is 2. 2 minus 2 is 0 over 0, so it's indeterminate. There's a radical, so that's probably going to tell us to use rationalizing. So let's rationalize this by multiplying by the conjugate. 2 plus square root 4 minus x. Multiply the bottom by the same. Square root 4 minus x. Limit as x goes to 0. So you got to expand the numerator because you're rationalizing. So 2 times 2 is 4. Because they're conjugates, middle terms will wipe each other out. All you got to do now is multiply this one by this one. So it's always negative times positive. So that's going to be negative. Here's the key that students run into here. When you multiply this radical by this radical, it gets rid of the radical. However, you need to make sure you put it in brackets. If because if you don't, this negative will not distribute in here the way it's supposed to, and you'll get the wrong sign on this one. It's a really common error. The bottom, don't expand it out, just leave it. So it's x, and then 2 plus square root, or subtract x. Okay, let's see what I get in the numerator now. Tidy that up. Limit as x goes to 0. 4, take away 4, that's 0. This negative will go in here, and this will become x. You'll often get students that have the wrong sign there because of what I just explained up above. Perfect. There's an x down here, bracket, 2 plus square root, 4 minus x. Close that off. Gone. There's your problem fixed because those are both zeros. X was getting close to 0. 1 left there. Now substitute 1 over 2 plus the square root of 4 is 2. Final answer, 1 over 4. That's your first one. Again, should be a dead giveaway in this one. Fractions within a bigger fraction. Use common denominators. Limit as w goes to 5. Common denominator of w and 5 is 5w. First fraction I have to multiply by 5. Second fraction I have to multiply by w. Now, rather than dividing by that, we're going to multiply by the reciprocal. Now, you may notice that this, so 25 minus w squared would go here, but that's difference of squares. So let's factor it as we write it out. So rather than writing it that way, I'm going to write it as 5, the factored form. 5 subtract w, 5 plus w. Well, this is the problem factor because if w is 5, that's 0, that's 0. Perfect. That and that. Now, this time they're in the exact same order. So when I cross those out, divide them out, we're going to get a positive 1, not a negative 1. Make w go to 5. So in the numerator, there's nothing left but a 1. 5 times 5, that's 25. 5 plus 5, that's 10. Final answer, 1 over 250. Bottom 2. Well, we've done one very similar to this back on a slide ago. Difference of squares. Let's use factoring. Limit as x approaches a. Square root of the first is x plus a. Subtract the square root of 4a squared, which would be 2a. That's the first factor. Square root of the first plus square root of the second. No factoring available in the denominator. So we're hoping to somewhere find a factor up amongst these that is equal to x minus a, so I can cross that out. Again, that's what I mentioned earlier about anticipating what should happen, so that if it doesn't, you can try and find your mistake. Let's see what happens here. X plus a minus 2a. Perfect. X minus a. X plus a plus another 2a, that's x plus 3a. But we know we're in business now because that is going to cross that one out in the bottom. And I can see that before I even do cross them out. Cross these two out. I get a 1. So 1 left here. Final answer. Put a in for the x. So a plus a is 3a times 1. Sorry, it's 4a. 4a over 1. There's your final answer, 4a. Last one. Definitely some factoring here. Sum of cubes, simple trinomial. Let's see where that goes. Limit as x is approaching -3. So sum of cubes on this would be cube root of the first plus cube root of the second. Square this one. Product, opposite sign. Square this one. Two numbers that multiply to give -6 and add to give 1 would be a +3 and a -2. X plus 3, x minus 2. So getting to the point now where we're starting to get the hang of these, we should be excited to see what just happened. Those are the same. Perfect. Those were the two causing problems because if x was -3, that was 0 and 0. Those have now crossed each other out to give us 1s. And we simply put -3 in for all the x's. So -3, now you got to make sure you realize this is, you can say, well, there's no brackets there. It's understood to be in brackets. So -3 in brackets squared is 9. Negative 3 is 9, plus 9. Negative 3 take away 2 is negative 5. Final answer, 27 over negative 5. Remember, the negative could be here. Sometimes people just put it out in front in general. Those are all the exact same thing. There you have it, your checkup quiz solutions. All right, so at the end of this video, you should now be getting comfortable with evaluating limits that are either direct substitution. Just did 2 quick examples of that. As you saw, there wasn't even any of those on here because they're extremely easy. Or what are called indeterminate limits, which is a primary focus of limit work in any calculus course. All right, stay tuned for the next video, which will look at some special cases of limits. But it's really important that we get our brain wrapped around these, so there'll be some practice questions to follow.